multiply matrix A with matrix B. When you do the multiplication of matrices, keep in mind order doesn't matter. Who's staying in the front is a key component, and you don't swap the order. So this one, we have the matrix A stay in the front. I mean, we use the row of matrix A to multiply with the column of matrix B. And it always has that same pattern. Row on the first matrix to multiply column on second matrix. So we start on the row 1 on matrix A to multiply with the column 1 on matrix B. So we use a 1 multiplied by 1. I'm going to put a 1 multiplied by 1. The number from the column, I use a parenthesis to round it, plus 2 multiplied by negative 2. So 2 times negative 2 plus 4 multiply 1. Now we move on to the row 1, column 2. The row 1, we have the 1 multiplied by 5 plus 2 multiplied by 4 plus 4 multiplied by negative 3. So here you can see the number I rounded, they all represent the column number. We have finished the row 1, now we move to the row 2. So the first entry on the row 2 of matrix A has negative 2. Now we multiply with the column 1, which is 1, plus 1 multiply negative 2, plus negative 1 multiply with 1. Now we move to the column, the row 2, column 2. So we take a negative 2 multiplied by 5 plus 1 multiplied by 4 plus negative 1 multiplied by negative 3. Now we've cleaned up the calculation here. Here we have 1 minus 4 plus 4, which is 1. 5 plus 8, we have 13 minus 12. So 13 minus 12, we have 3. Sorry, 13 minus 12 is 1. Negative 2 minus 2, we have minus 4. Then minus 1, we have minus 5. Negative 10 plus 4, we have negative 6. Negative 6 plus 3, we get a negative 3. So the product of the matrix A and B, it gives us a new size matrix, has 2 by 2. And that it's the same dimension we just determined earlier. And the output of the new product matrix has 1, 1, negative 5, and negative 3. The multiplication of matrices is not cumulative. That means order you don't swap. Who stay in the front doesn't matter. As here you can see, matrix A is 2 by 2, B is a 2 by 2. But when I use the matrix A to time matrix B, the outcome has 0, 2, 0, 0. And the reason they get a 0, 2, 0, 0, if you use a row 1 multiplied by column 1, you will get 0, 0, right? Row 1, column 1, everything is a 0. Row 1, column 2, you'll have 1 plus 1, which is 2. Row 2, column 1, since everything has 0, so you get a 0. Row 2, column 2, since you have the 0 here, multiply 1, you still get a 0. When you use a matrix B to multiply by matrix A, so the order swap, the new output of the matrix it give us is a 0, 0, 0, 0. Because row 1, column 1, you have 0 multiply 1, you get a 0, plus 1 times 0, you still get a 0. Row 1, column 2, 0 multiplied by 1, you get a 0, plus 1 multiplied 0, you get a 0, so stay 0. Row 2, column 1, you have the 0 plus 0. Row 2, column 2, you get a 0 plus 0. So you have all 0 by the end. So since the products are not equal, matrix multiplication is not cumulative. Alright, so that I mentioned earlier. Who's staying the from doesn't matter. Recognize the identity matrix. That A matrix A has n by n. There is an n by n identity matrix I for which, when you use the matrix A to multiply the identity matrix, is equal to identity matrix to multiply with the matrix A, and you will go back to the matrix A itself. For example, when I have the matrix A is 1, 2, 3, 4. This is a 2 by 2. The identity matrix of the matrix A must have the same dimension of this matrix. So it's 1, 0, 0, 1. It's a 2 by 2. So when you multiply matrix A with the identity of the matrix, this is what you call the identity matrix to multiply with the matrix A. It will go back to the matrix A itself, which means it's the same idea. When you have the 4 multiplied by 1 is equal 1 multiplied by 4 is go back to 4. So identity matrix has the same idea, it's just like the number 1. But the matrix matrix I has the matrix arrangement. It's a scale arrangement, not just a single number 1. The characteristic of the identity matrix, it must be a square matrix. So 2 by 2, it must be a square. Okay. Square matrix. So it must be 2 by 2. I will start on 1 by 1 because 1 by 1 is a square matrix as well. So your identity matrices could be 1 by 1, which is you only had a single element 1 inside. It could be 2 by 2. So when you have the 2 by 2 identity matrix, you will see the 1 and the 1, they are on the going down, decreasing diagonal direction. You will see the all element of 1. The remaining number has 0. 3 by 3 identity matrix. You will have the 1, 1, and a 1. So you have the 3 row, 3 column. So the remaining element, they are all the 0. So this is a 3 by 3 identity matrix. And you will see this direction, the going down diagonal direction, they all has the number is 1. We call identity matrix. On this slide, it just give you a property of the matrices. What type of the property you will see that when you work on matrices. So it has the commutative property. That means matrix A plus matrix B is equal B plus A. You can swap the order. When they add, when they subtract, no, you don't. Associate property, that means when you have three matrices combined, you can do the last two first. Is equal when you process the first two. But keep in mind, this is only go with addition, when you add a multiple matrix together. Associative property of scalar multiplication. So when you multiply a scalar A to the B, A and B to the matrix A, you can multiply the scalar B with matrix A. It is equal, you multiply these two scalar number and then you multiply with matrix A. Distributive property of scalar. So when you have the A plus B multiply with matrix A, this is equal A times matrix A plus B times matrix A. When you have the scalar A multiply with matrix A plus another B, same way you distribute it and you get an A times matrix A plus A times matrix B. So this is a typo. No wonder when I read it I feel like something is not right. Associative property of the multiplication. So when you multiply three matrices, you can multiply the last two first. And then go back to multiply with the first matrix. Or you can process the first two matrices and then multiply with the last one. Distributive property of the matrix multiplication. So matrix A multiply with B plus C, you can distribute it into the A, B plus AC, or the other way around. So we do an example to close, to associate with the example here. Verify the distributive property matrix A times B plus C is equal AB plus AC. So we have these three matrices. We do the left-hand side first. We use the matrix A to multiply B plus C. So we look at the example here. Matrix A has this matrix, B combined with C first. So when we sum these two matrices, the inner two matrices here, we go with the corresponding position. Remember that? So 3 plus -1, you have a 2. -4 plus 3, you get a -1. 1 plus 0, you get a 1. -1 plus 1, you get a 0. And then your matrix A stay in the front. Your order stay the same. Then we start to process the multiplication of matrices. We use the row 1 to multiply with the column 1. So let me do the procedure here. We put a row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. So row 1, column 1, 2 by 2 is 4, plus 1 by 1 is 1. Now we move to row 1, column 2. 2 multiplied by -1, you get a -2. 1 multiplied by 0, you get a 0. Now we move to row 2, column 1. So you have 3 multiplied 2, you get a 6. Plus 1 multiplied by 1, you get a 1. Now row 2, column 2, you have 3 multiplied by -1, which is -3. 1 multiplied by 0, you get a 0. Now we sum these two, you turn to the 5. Sum these two, you get a -2. Sum these two, you have 7. And then you have the -3. So this is the left-hand side. Now we process the right-hand side. The right-hand side, they distribute the A into matrix B, distribute A with matrix C. So we look at this example here, right? So this is matrix A times B plus matrix A times C. So we use the row 1 multiplied by column 1. You have 2 multiplied by 3 plus 1 multiplied by 1. and that's why you get a 7. Now we do the row 1, column 2.